Welcome to 3D Time, from Transportation to Physics. My name is Ralph Gilman, and this is Part 7, Relativity. We'll start with Galileo's relativity, or what's called Galilean relativity. He gives the example of being in a large ship that's going at a constant velocity, and comparing when the ship is at rest and when the ship is moving. If you're below deck and you can't see outside, and you try a few simple experiments. You throw something to a friend, and you put your legs together and jump up. Well, you'll notice that the motion is the same in all directions. So the conclusion is that constant velocity is relative. You can only tell what's moving relative to something else. This is expressed by transformations in space. We'll look at two frames of reference, S and S prime. And to be simple, let them coincide at time t or t prime equals 0. And that motion is only parallel to the x-axis, so that's the only motion considered. In frame S, it views S prime with velocity v prime, and frame S prime views frame S with velocity v in the opposite direction. Now say they both observe an event. What coordinates will they attach to that event? We'll also consider transformations in time. These are time frames now, t and t prime, and let them coincide at a beginning point, r equals r prime equals 0, and say that motion is parallel to the t-axis, which is one of the time axes. The other two are p and q. So time frame t views time frame t prime with linearity u prime, and time frame t prime views time frame t as having linearity u in the opposite direction. So they both observe an event. What coordinates will they assign to that event? So these are the Galilean transformations then. Galilei in 3D space. In frame S, we have that x prime equals x minus v, the velocity, times t, the time. And t prime equals t because time is considered absolute. And in frame S prime, x equals x prime plus vt prime. So that's in the opposite direction. And t equals t prime again. Space is relative and time is an absolute scalar. And then in Galilei in 3D time, the time frame t finds the t prime equals t minus the linearity times x. And x prime equals x, that is to say, the x-axis is considered to be absolute. Time frame t prime, t equals t prime plus the linearity times x prime in the opposite direction again, and x equals x prime. So in this case, time is relative and space is absolute. Now consider the Lorentz transformations. Both physicists Lorentz and Einstein are famous for this. Start with an absolute speed of light, c. This is constant from every frame of reference, and it's the maximum speed. Also, we'll have a spherical wavefront of light at distance r from s and r prime from s prime. So r equals c times time, and r prime equals c times t prime. Now we have frame S. In this case, x prime equals gamma, that's a gamma letter, times the x minus vt that we had before. And frame S prime has x equals gamma, x prime plus vt as before, in the opposite direction. So the Lorentz transformation works out to gamma squared being 1 over 1 minus v squared over c squared. And note that that makes sense only if v is less than c. Surprisingly, there's also a transformation for t. T prime equals gamma times t minus vx over c squared. So this is called a time dilation and length contraction. Now let's consider the Lorentz transformation in 3D time. Going back to Lorentz and Einstein, we consider the absolute pace of light, in this case, equals to the inverse of c. We'll call that c sedilla, which is constant from every time frame, and there is a minimum pace. We'll also consider a spherical wavefront of light of duration t from time frame t and t prime from time frame t prime. So in this case, we have t equals c sedilla times r, and t prime equals c sedilla times r prime. We're going to put this together in two ways. First, look at the time frame t with length. X prime equals gamma again, but x minus t over u, the linearity. And time frame t prime has x equals gamma times x prime plus t prime over u. So the Lorentz transformation in 3D time works out to be gamma squared is 1 over 1 minus c sedilla squared over the linearity squared, which it turns out is exactly the same as the gamma from before. And t prime similarly works out to be exactly the same as before, the Lorentz transformation in space. It's the same time dilation and length contraction. However, now let's look at the time frame t in duration. Start with duration. T prime equals, call it lambda times t minus u, the linearity, times x. And the time frame t prime has t equals lambda times t prime plus ux prime. So we work it out as before, it's just algebra, and it works out that lambda squared equals 1 over 1 minus u squared over c sedilla squared, which, if we put it back into speed, is 1 over 1 minus c squared over v squared. Now, we notice that that makes sense only if v is greater than c. And there is a value for x prime equals lambda x times ut over c sedilla squared. So this works out for speeds greater than light, which perhaps do not even exist. We'll have to look at the one-way speed of light. It turns out that we measure the speed of light by reflecting light. So we really get two one-way speeds of light, and we take the harmonic mean to find the c, the average speed of light. Now we need a synchrony convention of some sort to define simultaneously 4 frames. And there are multiple ones available. By far, the one-way speed of light is considered to equal c by the physics community. In fact, it's defined as that. But it is possible to define the incoming or outgoing speed as infinite, and the speed of light the other direction as c over 2. This seems strange, but it is perfectly consistent with experiment, and we'll show what it leads to. The question, it turns out, is whether there is a qualitative difference between space and time. We start with the convention in 3D space. If we have an instantaneous incoming light, and then look at the Lorentz transformation, c approaches infinity, so gamma approaches 1, and t prime equals t. Well, this equals the Galilean transformation. So space is relative and time is absolute. And observation is considered instant. When we look at a star in space, we look at it as it is now. Now look at the convention in 3D time, instantaneous outgoing speed of light. So again, the Lorentz transformation, c approaches infinity, lambda approaches 1, and x prime equals x. So this is like a Galilean transformation, but time is relative and space is absolute. So this would be like an instant transmission of light. And the interesting thing is that this is the way we speak. We speak of stars as where they are now, and transmitting light as where it is now when we transmit it. We'll touch on general relativity by looking at equivalence principles. There is an elevator example used. If we're in an elevator and we detect acceleration down, well, is it gravity pulling things down or an acceleration pushing the elevator up? Well, strictly speaking, we cannot tell the difference if we're inside the elevator and can't look outside. Similarly, for expedience, we could talk about detecting expedience up. And is it levity pulling the elevator up or an expedience pushing things down? Well, again, we cannot tell the difference. And this is the basis for general relativity. In conclusion, we've looked at the Galilean transformation in 3D space and found that it means an instant observation, and the Galilean transformation in 3D time, which means an instant transmission. And then we looked at the Lorentz transformation in 3D space and compared it to the 3D time, which can be equivalent, but 3D time can also work for speeds greater than the speed of light. Then we looked at equivalence principles and found that they are equivalent for 3D space and 3D time. So hey, 3D time does relativity. Next is part 8, 6D space-time.